Hi, it's Dr. Harris, and we're back for the conclusion of our videos on Chapter 5 in our MAT111 statistics course. In the previous videos, the most recent videos, we've been talking about confidence intervals. And in this video, we're going to introduce our other primary inferential statistical technique in this course, and that is the hypothesis test. So just to review very briefly, a confidence interval was an interval of numbers on which we think a population parameter is likely to live. And in this video, we're going to examine a different type of question. In this case, we're going to say, if I take a specific possible value for the parameter, do or do not the data that we've collected support the notion that that might be our parameter value? In this chapter, we're talking about population proportions. So we, in our previous slideshow, we were looking at an example involving proportion of U.S. adults that can drive a manual transmission automobile. And suppose that we draw 500, a random sample of 500 such adults, ask them the question, can you drive a manual transmission? And what comes back is that slightly over 19% of the respondents say, yes, I can. And so in this case, when we're going to be looking at trying to talk about hypothesis testing, we would come to our data with questions such as these. Is it reasonable to believe, if I think that the true population proportion is 18%, is that reasonable? Or if I thought it was 15%, based on the data that we've collected, would that be a reasonable claim? So we're coming to our data collection with a claim about the value of a parameter. And then we collect some data, and then we're going to talk about in this section, what are some ways that we can investigate the question, is the value that we started off with thinking was the correct value, is it reasonable to believe that that might be the true value? And so what we're going to do in situations like this is we're going to form a couple of hypotheses. So we want to be looking at scenarios like this where, say, a researcher comes to say, well, I believe that the population proportion is 18%. Let me collect some data and see if that seems reasonable based on that data. We're really coming with two claims. One is that the 18% figure is correct, and the other one is that it's not correct. And so the null hypothesis is going to be the claim that the parameter that I've come to my data collection with is in fact the correct value. And so we're going to denote the null hypothesis by the symbol h sub 0, and it's going to be an equation. So a null hypothesis is an equation. It's saying that the parameter takes on a specific value. And if you read the text, you'll observe that they say that this claim often, not always, but often is going to be considered from what we might call a skeptical perspective. That is, we're not really quite sure that it's right. We're going to try to see if we have evidence that might disprove that that's a reasonable value. But other times we're interested in the question, is it really, I think this is right. Is it make sense to think that that's right? And we're going to oppose the null hypothesis with what we call the alternative hypothesis. And that's going to be denoted h sub a. And as I say here, this is going to be the statement that we accept if we decide that the null hypothesis is not a reasonable statement. And so the alternative hypothesis for us is going to be an inequality. Let's take a look at the types of inequalities that we might encounter. Not equal to, less than, and greater than are all variants of inequality. But in this course, we're going to be looking only at cases where the alternative hypothesis is not equal to. If there's time at the end of the course, we may look at an example or two where we examine alternative hypotheses where we're asking, is it reasonable to believe that the parameter is actually higher than the value we're claiming or lower than the value we're claiming? But in this course, in this set of videos, we're going to be strictly looking at examples where our alternative is that the value that we are claiming is just wrong. We're not proposing that it's bigger than the number we've come up with or less than, just wrong. And so the alternatives that we're going to be looking at in this course are called two-sided alternatives, parameter not equal to a value. If I had greater than or less than as my alternative hypothesis, then those would be one-sided alternatives. But again, that's something we'll come back to only at the very end if we have time. So let's form a couple of hypotheses based on a claim. A researcher believes that 18% of US adults can drive a standard transmission automobile. What are the appropriate hypotheses for this researcher? If we're strictly looking at two-sided alternatives, then the null hypothesis is going to be P. P is going to be our per population proportion. It's the proportion of individuals who can drive a manual transmission. And so the null hypothesis is going to be P equals 0.18. And our two-sided alternative will be P not equal to 0.18. And so we call the number that's present in the null hypothesis the null value. So 0.18 is our null value. And as I note here at the very bottom of the slide, we are going to strive to define our parameters in terms of words before we begin anything with respect to confidence intervals, hypothesis tests, whatever. We want to focus on being able to write down, represent in words, what the parameters under study are in a given scenario. So we're going to look at, in this slideshow, two different techniques for testing hypotheses. And as I note here, the first one is going to involve confidence intervals, in particular 95% confidence intervals for starters. So based on what we saw in the last slideshow, we can compute a 95% confidence interval once we've collected a random sample and gathered data from that sample. That's presuming, of course, that the success-failure condition is met, that we have at least 10 successes and 10 failures. And as I note here, a confidence interval gives us a range of values that we think are reasonable choices for the value of the parameter. So if the confidence interval gives us reasonable choices for the parameter's value, then sort of a quick way, once we have a confidence interval, a quick way to test a hypothesis is really just to ask, is my null value on the confidence interval or not? If the null value is on the confidence interval, then as I say here, we're actually not going to say the null hypothesis is right. We're just going to say we didn't find any evidence that the null hypothesis is wrong. In other words, we're going to say that we fail to reject the null hypothesis. So again, if we have a confidence interval constructed, we're just going to ask, is my null value on the confidence interval? If yes, then we're going to fail to reject the null hypothesis. We're going to say that we didn't find evidence that the null hypothesis was wrong. So in particular, we're never, ever, ever going to say we accept the null hypothesis. Please, in your write-ups, don't do that. If instead, though, that the null value is not on the confidence interval, then we would say that the null value is not a reasonable choice for the value of the parameter, and so therefore we will reject the null hypothesis. So our two choices are going to be reject and fail to reject the null hypothesis. So using a confidence interval, null value on the confidence interval, fail to reject. Null value not on the confidence interval, then we reject the null hypothesis. So let's look at our previous example. 500 US adults sampled, 96 of them, 19.2%, say they know how to drive a standard transmission car. If you go back and look at the previous slideshow, we found that the confidence interval for the proportion of US adults nationwide that could drive a standard transmission was somewhere between 0.158 and 0.226. So if our null value is 0.18, if our null hypothesis is P equals 0.18, since 0.18 lives between those two numbers, we would not reject the null hypothesis. We would fail to reject and say we didn't find evidence that 0.18 is a bad number. It should be rejected. If, on the other hand, we came into our data collection saying that we thought that it was only 15%, then since 0.15 is not on the confidence interval, we would reject that null hypothesis. So again, if we have a null value and a confidence interval, we're just asking, is that null value on the interval? If yes, fail to reject the null hypothesis. If no, then reject the null hypothesis. But we'd like to actually come up with a way of testing hypotheses that doesn't involve any confidence interval calculation. So let's see what we can do about that. And so what we're going to do for that is we're going to calculate what we call a p-value for the statistic that we have collected from our data. And so we need to define what we mean by the term p-value. Okay, so we've stated a null hypothesis, and the logic of a hypothesis test is going to be that we believe we're going to act as if the null hypothesis is correct. So we've got our null and alternate hypothesis set up. We're going to behave, we're going to proceed under the assumption that the null hypothesis is correct, and then we're going to see whether or not that seems reasonable or not given what we find. So here's our definition of p-value. So once we've got our null and alternative hypotheses, the p-value is the probability of observing data at least as favorable to the alternative hypothesis as the data that we collected, under the assumption that the null hypothesis is in fact correct. So p-value is a probability. And so it's going to be the probability of obtaining the sample statistic that we did that's that far from our null value or farther. So what we mean by as favorable to the alternative hypothesis as our current data value is it's the probability of getting the statistic as far away from our null value or farther in a world where the null hypothesis is assumed to be true. So if a p-value is a probability, we know that large probabilities are values that are events that are likely to happen. Small probabilities are events that are unlikely to happen. So the smaller the p-value, the less likely it is that our null hypothesis is true. The smaller the p-value, the less likely, the stronger the evidence that the null hypothesis is correct. So what's left to do then is to figure out how we're going to calculate the p-value. And we're going to use our friend from chapter 4, pnormgc, at least for the time being. pnormgc is going to be the RStudio command that we're going to use to find the p-value. That's not going to work when we get to chapter 7, but for right now here in chapter 5 and a good part of chapter 6, we're going to be using pnormgc. So here's how we're going to use pnormgc to find p-value. So if we have collected data, we've got a sample statistic, we know something about the distribution of p hat under the assumption that the null hypothesis is true. So if our null hypothesis were that the proportion of US adults that can drive a standard transmission automobile is 0.18, then from back when we saw from our sampling distribution activity that the distribution of p hat will be approximately normal, will be centered at 0.18 because we're assuming that the null hypothesis is true. And the standard error then is going to be the square root of 0.18 times 1 minus 0.18 or 500, which we actually computed a couple of slideshows ago, a couple of videos ago as 0.0172. So these calculations, the mean of 0.18, the standard error of 0.0172, are all based on assuming that the null hypothesis is true. So again, we're proceeding as if that's the case. So once we've got a mean and a standard error, we can begin moving toward calculating the p-value using pnormgc. So how do we do that? Well, 0.192 is 0.012 above the hypothesized proportion. It's above 0.012 above the null value. So in this case then, to be as far away or farther from our null value means that we would be either 0.012 above or 0.012 below the hypothesized value, our null value. And so what we have to do is we have to do a little bit more arithmetic. Since 0.192 was 0.012 above 0.18, we need to calculate the number that's 0.012 below 0.18. And you can see I've done that subtraction here on the slide. We get 0.168. And so being as far away or farther from 0.18 in this instance would mean that we're either below 0.168 or above 0.192. So again, let me try to say that. If we want to know, if we want to be favorable to the alternative as the sample data we've collected, that is, if we're as far away or farther from the null value as our sample data, then that means that we're going to be more than 0.012 below or more than 0.012 above 0.18. And so that means that our sample proportion is going to be either below 0.168 or above 0.192. If you recall from chapter 4 how we use p-norm GC in a situation like this, we have choice of 4 different regions: above, below, between, or outside. Which one of those is the one that we want to use here? I'll let you think for about 5 seconds. Okay, time's up. Hopefully you recognized that this is a case where we're going to be going outside. And so we want to know what's the probability of landing outside the interval from 0.168 to 0.192. We see in our graphic that the shaded region consists of all the outcomes that are below 0.168 or above 0.192. And we see that the shaded area in this case is just a shade under 1/2, about 48.5% of the area underneath our normal curve. And so that means that our p-value in this case is 0.4854. That was the probability of landing below 0.168 or above 0.192. And so once I've got the p-value, how am I going to decide whether or not I should reject or fail to reject the null hypothesis? And the standard that we've come up with, that social scientists, natural scientists have come up with, they've agreed on a convention for when to decide to reject the null hypothesis. And that's going to be the case where the p-value is less than 0.05. So we'll come back and talk about that in a few minutes. But for right now, the first thing we're going to do is we're going to look at our p-value and ask, is it less than 0.05 or is it greater than 0.05? If it's less than 0.05, that's going to be a signal that we should reject the null hypothesis in favor of the alternative. But if it's bigger than 0.05, we're going to fail to reject the null hypothesis. So again, we're not accepting the null hypothesis. We're failing to reject it. We're just saying we don't have evidence that doesn't support it. And as I say here, that the data that we collected seems to be consistent with a world in which the null hypothesis is actually correct. So what is this 0.05 standard? So just applying it in this particular case, our p-value was 0.4854. And so I've written a sentence here that interprets that number in context. If the proportion of US adults who can drive a manual transmission is 0.18. So that if phrase is just a restatement of the null hypothesis. So if P is 0.18, if the proportion of US adults who can drive a manual transmission is 0.18, then the sample data collected provided us with a sample proportion such that it, or one farther away from 0.18, would occur about 48.5% of the time. Since 0.485 is bigger than 0.05, we're going to fail to reject the null hypothesis. So we don't have evidence that 0.18 is a bad number to choose for this proportion. We did not collect evidence that disputed the claim. So again, the first pass on things, we calculate a p-value, in this case, using p-norm GC, and then we ask, is the p-value bigger than 0.05? If so, fail to reject the null hypothesis, but if it happens to be less than 0.05, we're going to reject the null hypothesis in favor of the alternative. Okay, so just a quick other example. Suppose that our null hypothesis had been p equals 0.15. Let's go ahead and compute a p-value in that case. So if the null hypothesis is true, then the distribution of p hat would be centered at 0.15, and the standard error would be the square root of 0.15 times 1 minus 0.15 over 500, which is a little bit smaller number, about 0.16. 0.192 is 0.045 above the null hypothesis. And so if we want to figure out if we're 0.042 or farther away, we need to find out what number is 0.042 below our null value. And so we compute the difference 0.15 minus 0.042, and we get 0.108. So in this case, being as far away or farther from the null value as our sample data would mean we're being outside the interval from 0.108 and 0.192. So our p-value in this instance then is about 0.0087, less than 1%. Okay, so the statement that we would use to interpret our p-value this time is, if the null hypothesis is true, if the proportion of US adults who can drive a manual transmission is 0.15, then the data that we collected gives us a sample proportion such that it, or one farther away from 0.15, would occur about 0.9% of the time. And that's not 9%, that's 0.9%, less than 1% of the time. Since 0.0087 is less than 0.05, we are going to reject the null hypothesis. And we'll say that 0.15 is not a reasonable value for the null value, for the population proportion. Okay, so before I go in and say a little bit more about this 0.05 bit, let's reconnect with the confidence interval thing. So we've done this problem two different ways, using confidence intervals and using p-values, and let's notice that they agree. In the first case, when our null value was 0.18, 0.18 was in the confidence interval, and we failed to reject the null hypothesis. And so, but if the so that was what happened in the first example. 0.818 was in the confidence interval, and we failed to reject the null hypothesis because the p-value was bigger than 0.05. On the other hand, the second example, where p was 0.15, 0.15 was outside the confidence interval, if you recall, and it also was the case that we rejected the null hypothesis, that 0.15 was not a reasonable choice for the parameter. That's how it works. If the null value is in the confidence interval, we're going to fail to reject. If it's outside the confidence interval, we're going to reject the null hypothesis. Okay, so let's again talk a little bit more about what exactly is going on here. P-values are probabilities. And so we know we're always going to be calculating a probability associated with the likelihood of obtaining the statistic that we did, or one farther away. And so there's a continuum of values. The probability could be any number between 0 and 1. And we have to decide at what point are we going to say that the probability that we've obtained is just too small for it to be reasonable to believe that our null value is correct. In other words, no matter what the probability is that we calculate, we're having to make a choice. We're having to be making a choice whether the sample data we collected speaks against the null value, or was simply an unlucky sample to be chosen. And so we're making a decision: unreasonable choice for null value, or unlucky sample chosen. And so the p-value is a number between 0 and 1. We have to decide how small the p-value should be before we tip our thinking over and saying that speaks too much against the null value, rather than this could be an accidentally bad sample, an accidentally unlucky sample. And the number 5% is the place where a lot of scientists, both social and natural, have come down on landing and saying that that's just the place where the break point between saying unreasonable versus unlucky. We're going to say that we're not unlucky if our p-value is below 0.05. We're going to say that it's unreasonable to believe that the null value is what we claimed it was. But because it's a probability, we might be wrong about that 5% line that we've drawn. It could be that we truly have drawn an unlucky sample. And the idea, as I've noted here, is that unlikely events do occur from time to time. If we're talking about an event that occurs with frequency 0.05, it happens 1 in 20 times, 1 every 20 times. And so if we're using the 0.05 standard to make a decision about the null hypothesis, we need to recognize that we are making an incorrect decision 1/20th of the time. And that's just something we're going to have to live with. No matter how small we made the p-value, no matter how small we made the threshold for failing to reject the null hypothesis, we're going to be making a mistake some fraction of the time. We've decided that we're willing to live with being wrong 5% of the time about rejecting the null hypothesis. But we would be making an error in those cases. And the name we give that error is type 1 error. So when we reject the null hypothesis, when the p-value is less than 0.05, but the null hypothesis was actually correct, we're making what we call a type 1 error. And so if we use the 0.05 standard, the probability of making a type 1 error is 0.05, 1 in 20. There's another type of mistake that we could make, though. We could fail to reject the null hypothesis when we actually should. And that type of error is called a type 2 error. We're not going to talk about how to calculate probability of making a type 2 error in this course. But just let me restate things. Type 1 error is when we reject the null hypothesis when we shouldn't. Type 2 error is when we fail to reject the null hypothesis when we should. So let's work through an example where we actually articulate what type 1 and type 2 error are. So you're a pollster, and you want to determine whether or not there's a majority of the residents in a particular state who will vote for or vote against a particular amendment to the state constitution that's coming up in this fall's election. Let's first describe come up with the parameter in words that we're trying to measure in this case. Give you a couple of seconds to think about this. It's a population proportion. Okay, here we go. Let's use P as the proportion of residents in the state who plan to vote for the amendment. Now, there's the choice of vote for was a little bit arbitrary. We could have just as well put vote against here, but we'll just say we'll be sort of positive about this. What's the proportion that plan to vote for the amendment? Okay, so next thing is what we want to do is we want to form hypotheses. Let's go back and think about our question. The pollster is trying to determine whether or not there's a majority of residents who plan to vote for or against the amendment. Okay, so majority means more than half. So do more than half favor it or do more than half oppose it? So that suggests that 1/2 should be our null value. So the null hypothesis is going to be p equals 0.5. And our alternative, which is two-sided, is going to be p not equal to 0.5. Last thing we're going to do in this slideshow is we're going to describe in words type 1 and type 2 errors. So since type 1 error is rejecting the null hypothesis when we shouldn't, then type 1 error is going to be claiming that there is a majority position on this issue, that either a majority favor it or a majority oppose it, when in reality it's split down the middle. So rejecting the null hypothesis is saying that, or falsely rejecting the null hypothesis is saying that we think that there's a majority position in the state even when there's not. Whereas type 2 would be failing to reject the null hypothesis when we should. And so in this case, we would be claiming that 50-50 is a reasonable position, is a reasonable place where the state is, even though there really is a majority one side or the other. You'll get your chance to look at type 1 and type 2 error in exercises coming up.